Okay, good afternoon, everybody, and welcome to the 13th Eurados webinar, which is dedicated to small photon beam dosimetry. My name is Hrvoje Hršak, and as a coordinator of a small photon beam dosimetry task of Eurados Working Group 9, I would like to thank you all for attending this webinar, which will be, I believe, very interesting for the researchers and for the clinicians as well, because the topic is hot, I would say. In this webinar, we will address some of the issues and the current status of small beam dosimetry. And for that, we have two prominent experts in the field. These are Božidar Casar from Department of Dosimetry and Quality of Radiological Procedures, Institute of Oncology, Ljubljana, Slovenia, and Josef Novotny from Department of Medical Physics, Nahomolce Hospital, Prague, Czech Republic. So the rapid evolution of treatment delivery techniques brought modern radiotherapy to a stage where more complex and sophisticated machines and treatment strategies are used, which leads to more precise delivery of radiation dose to tumors and better sparing of healthy tissue. So techniques such as SRS, SRT, IMRT, VMAT, they all use small photon fields down to 4 millimeter in size. But however, compared to classical radiotherapy photon fields, which have size bigger than 3 centimeters, and we know that the reference size is 10 by 10 centimeters, dosimetry of small fields is associated with the detector volume averaging effect, high dose gradients, lack of lateral electronic equilibrium, source occlusion, and some directional orientational problems with detectors, which makes dosimetry more challenging. The literature addressing the field brought many different results for different detectors, sometimes even controversial. And it is up to a couple of years ago, no national or international recommendations for small field dosimetry were available until IAEA and APM jointly published Code of Practice TRS 483. But however, as new types of detectors are emerging and some controversy is still present in the small field dosimetry formalism, there is a need for additional reference data for detectors to be efficiently and safely used in the clinic. So two main presentations today will address these questions, but before we start with that, let me give you a short overview of the Eurados Working Group 9 activities. In Working Group 9, researchers from many European laboratories, universities, and clinics are working together to develop different research programs in radiation dosimetry and radiotherapy. And these activities are directed toward development and assessment of dosimetry techniques for non-target patient doses in X-ray and proton therapy, which we call out-of-field doses. Then determination of the total dose to the patient from therapy and imaging in collaboration with the Eurados Working Group 12, specific developments in proton and neutron dosimetry, in phantom and ambient neutron dosimetry and spectrometry, fetal dose determination, which is one very important activity, Monte Carlo simulation studies to support and enhance experimental programs, identification of new and emerging dosimetry techniques and materials, and of course, one very important topic that is a small beam dosimetry. And these activities are actually divided into task group programs, which are, we can say there are 3 of them. The first is photon radiotherapy program. It has 2 tasks, that is a small field photon beam dosimetry and out-of-field doses in brachytherapy. Then the second program is computational methods in medical physics, in which there are 3 tasks: dose to fetus during radiotherapy, secondary radiation for superconductive synchronous cyclotron, and normalization of secondary radiation doses in spot scanning proton radiotherapy. Especially this program is designed to enhance and to help other experimental measurements by simply giving mathematical or computational support, especially in the form of Monte Carlo simulations. The third program is Hadron Radiotherapy program, which has 3 tasks: dosimetry audit of active scanning proton beams, secondary radiation for superconductive cyclotron, in collaboration also with the Eurados Working Group 11. And the third task is normalization of secondary radiation doses in spot scanning proton radiotherapy. So these are all task programs which are covered now by the Working Group 9. And I will shortly, before we go to the main presentation, I will shortly present you the small mini task which is in the focus of the small beam dosimetry task. And that is the high resolution dose profile measurements for like cell gamma knife using point detectors. And I think I have jumped over the one presentation. Yes, so this Photon small field dosimetry program has 3 mini tasks, and these are in the comparison of small detector characteristics or responses, small field detector characteristics or responses, comparison of published code of practices, and machine and detector specific mini projects. Now we have in focus these mini projects. And one of these, which is nearly finished, is high resolution dose profile measurements for like cell gamma knife using point detectors. And we also have planned some other mini projects, which are angular dependence, research of the angular dependence of detectors in small photon fields, end-to-end test in stereotactic radiosurgery, 2D radioluminescent sheet dosimetry of the small fields. And also for the further planning, for the further plans, we have in mind the small photon beam dosimetry audit. For this first mini project, motivation was the fact that dosimetry for gamma knife radiosurgery beam profiles requires detectors with high spatial resolution. For that, radiochromic film is widely recommended, but in many papers, but no specific recommendations were given in the IAA TRS 483 code of practice, although AAPM report TG 178 recommends the film. But we wanted to see if there is a possibility to use another type of detector, point detectors, to do the profile measurements with the gamma knife. Because when you compare the point detectors to the film, okay, film has a high resolution and tissue equivalence, but the films are generally expensive, they could be noisy, and they require complicated workflow. You have to do the calibration, you have to do the measurements, have to wait for the saturation, do the evaluation. And of course, the films are spendable. After you do the measurement, you have to buy another film. So not all institutions are available to do that. Each time you need a film for the measurements. So for the methodology, we proposed a simple method for dose profile scanning using different point detectors in a non-reference geometry where spherical phantom with detector was moved from one measuring point to another. And this method was already tested. That's nothing new in this method. This method was already tested with the X-radin plastic scintillator detector. And we wanted to see how this method works for commercially available point detectors, which can be found in many, if not all, medical physics or clinical departments or research laboratories. And these are PTW and IBA small volume detectors, semiconductor and ionization chambers. We compared the measurements with Elekta reference profiles for the gamma knife, profiles obtained with the EBT3 film, and the profiles which were simulated in the non-reference geometry using the treatment planning system. And we found excellent agreement for diode and micro diamond detectors for both vendors. And that was something that was promising. How the measurement looked like. Here you can see the measurement set up using the ABS, so-called acetylbutadiene styrene phantom of Elekta, which was delivered together with the gamma knife, just to see how the measurements at the first point could look like. The phantom with the detector was moved in the small steps with a resolution of 0.2 millimeter in the 3 orthogonal principal axes of the system. On the right side, you can see the principal scheme of the measurement setup, you can see that small yellow billets entering the phantom in the non-reference geometry have different paths of attenuation. So we were wondering whether this method in non-reference geometry could provide us with usable profiles. So for that purpose, we first did a simulation of the non-reference geometry and compare it against the reference geometry using the TPS. And for the gamma knife, for the largest collimator, 16 millimeter collimator, we found excellent agreement. And at that point, it was actually very promising for the future measurements. After that, we decided we will use the solid water phantom for the measurements, and this is the Electa spherical solid water phantom, which is also delivered together with the gamma knife system. And for this phantom, the vendor will provide you only maybe 1 or 2 inserts for accommodation of the standard ionization chambers. But if you want to measure, if you want to use other point detectors, you have to produce the adequate inserts by yourself. So we decided to produce the 3D printed inserts, and according to our drawings, it was done in collaboration with the Faculty of Mechanical Engineering and Architecture in Zagreb. And here on the image you can see how these inserts looked like. We generally use the clear view resin material because it was easy to handle and easy to produce the accurate insert without any air bubbles. So after preparing this setup, we obtained the first results. Here you have for the largest collimator comparison of the Z profiles of Electa reference profiles against profiles measured in non-reference geometry with the diode E and with the pinpoint in the Z direction. Why Z direction? In Z direction of the gamma knife, there is a very steep dose gradient, and you can expect if you can count on, you can expect a significant volume averaging effect. But for the diode E, which has a very small measuring volume, practically there was no volume averaging effect. While with the pinpoint chamber, you can see that this effect was present. We did the same for the smallest collimator, 4 millimeter collimator in the Z direction. And also you can see that for the diode E, results were excellent. And for the pinpoint chamber, there is a significant volume averaging effect. We did the same with the IBA detectors. This is Electa versus Razor diode in the Z direction, and Electa versus Razor chamber, which is, I would say, close to the pinpoint, in the dimensions close to the pinpoint chamber. We did the same for the 4 millimeter collimator, and practically the results were the same as for the PTW detectors. So actually, just to little bit speed up, we measured 72 profiles for the gamma knife icon, and in total we have used 8 point detectors from IBA and PTW. We spotted less noise in the measure signal, reusability, and simpler pre-post processing, and this has advantage of point detectors over the radiochromic film, except for the ionization chambers, for which we saw the significant volume averaging effect. And we see that non-reference geometry proved to be good method for profile measurements during commissioning and quality control of the gamma knife. And because of the very small sensitive volumes of these detectors, which make volume averaging negligible, point detectors represent actually a good alternative to EBT3 for the gamma knife dose profile measurements. While at the same moment, profile measurements with ionization detectors, ionization chambers show volume averaging, so they are not to be recommended for the dose profile measurements. And results of these mini projects are now being prepared for publishing. So this was a little small or short overview of one of the mini tasks, mini projects of the small field dosimetry task of the working group 9. And now we will go to the two main presentations, for which I believe there will be great interest. First will be presented by Assistant Professor Božidar Casar from the Department of Dosimetry and Quality and Radiological Physics in Ljubljana. So, Božo, now I give floor to you.
Thank you very much, my dear friend Hrvoje. It is my privilege to be here today, and thank you for inviting me for this interesting topic. It would be impossible in half an hour to describe all the issues covered in the TRS 483, but I will try to do the best. As it was already pointed out a couple of years ago, 2017 to be exact, TRS 483 was published because actually the development in radiotherapy was huge in the last 2 or 3 decades, including some advanced radiotherapy techniques, stereotactic radiosurgery, stereotactic body radiotherapy, volumetric arc therapy, and so on. And there was no dosimetry protocol designed for small beams. At that time, there were various protocols, international, national, which were designated for broad beams, TRS 398, published in 2000, or TG51 for APM, and so on. But they do not provide guidance for dosimetry sorry, in small fields. And misunderstanding of this concept led to several clinical accidents, very serious also among them. And it resulted actually in TRS 483 aiming to cover all these aspects of small field dosimetry. However, as it was underlined by the authors of the protocol, the data available at that time were mostly for 6 MV beams, photon beams, also for 10, but mostly for 6. The various research groups took different approaches. Some were reporting nominal field sizes, some were reporting dosimetrical field sizes, some were measuring under SSD geometry, some SDD, and there was actually also a lack of estimation of the uncertainty. A proper estimation of uncertainty was missing in many of those studies. However, the need was so huge that the protocol was published in 2017. So when we can say that certain particular field is small, so at least one of 3 basic conditions should be fulfilled. 2 of them are beam related conditions and 1 is detector related. If there is a loss of lateral charge particle equilibrium on the beam axis, then we can count that the beam is small. Or if there exists partial occlusion, actually geometrical sheathing of the primary source, then also we can say that certain beam is small. And the last one is detector related small field condition. It depends on the size of the detector. And it was pointed out in the previous lecture, there is no such ionization chamber or detector that can be, let's say, that we can think of such a detector as ideal. There is a volume averaging effect always present. So, loss of lateral charge particle equilibrium, it actually means only that the outscatter from the beam is not compensated by the inscatter. If this is the fact, then we can treat beam as a field as a small. As long as water collision karma is equal to dose to water, the beam can be treated as broad. If the water collision karma is not equal to absorb dose to water, then we have a loss of lateral charge particle equilibrium, And actually, in two nice studies, they found a very simple expression which depends on energy. These were Monte Carlo studies. One was very early, more than 20 years ago, and one more recent from Papakostadopoulos from McGill. And the relation, which is actually a kind of limitation for a small beam, that one field can be treated as a small field, is actually very simple. And the parameter is called range of lateral charge particle equilibrium. So we need to know that we can use particular detector, particular ionization chamber, as it is a broad beam if this condition is fulfilled. The second one was source occlusion. So actually it means that the source of the photons is actually covered by collimators, and it has an effect of overlapping penumbras. In another figure, you can see that the consequence of this overlapping is lowering the output and broadening the penumbra, which was also nicely presented by Dr. Hershak in previous lecture, where volume averaging plays an important role. It is connected. These two, partial source occlusion is one effect, and the similar effect, very similar outcome, is with volume averaging effect, because any detector will average the dose across its sensitive volume, because it's not a point detector. It has certain volume. Even small diodes have certain active volume, and of course ionization chambers. And these volume averaging effect lead to dose underestimation, which is very important effect, and broadening of the penumbra. So you can see if we have, let's say, ionization chamber, the true profile of the field would be in red, and when the dose is averaged across the volume, then we get lower maximum and a little bit broader penumbra. It depends, of course, on the volume of the ionization chamber or solid state detector. It doesn't matter. So what is the actually content of this TRS 483 code of practice, dosimetry protocol for small fields? It provides guidance for reference and relative dosimetry in small static fields used in radiotherapy. In addition, it recommends various detectors which are suitable for reference and relative dosimetry, and provides formalism, which is based on the work of Alfonso et al. Slightly modified. It was published, I think, in 2007 or 8 already. And perhaps most important one, it provides detector-specific output correction factors for many solid-state detectors and ionization chambers. This is just a copy from the paper of Alfonso et al. Among them, there are also authors of the TRS, like Pedro André or Saiful Haq. So what is the basic concept? So if you remember, the various research groups took various approaches in their studies. One reported nominal size fields, one reported dosimetrical field size. There was not coherence also regarding the setup. So the TRS 483 defines a field site as a pair of dimensions, dosimetrical in this case. In the case of rectangular or also circular fields, that defines the area of the field. So it is now unique. It is dosimetrical field size. Each dimension is defined by full width at half maximum, And it is very important for small fields because dosimetrical field sizes and nominal field sizes can differ a lot in the case of very small fields. But it is still advised to record also nominal field sizes because it is usually used by treatment planning systems. The other important segment which is covered in the TRS 483 is definition of fields for field sizes. The one is conventional reference field size, which is used for calibration at the standard laboratory and used for Linux 10 by 10 because Linux can form 10 by 10. Then it's machine specific reference field. Probably it will be covered in the next lecture, which is defined for the machines which cannot form 10 by 10 reference field. And then is a clinical small radiation field at which we would like to determine the absorbed dose to water. So these three definition of fields are available in the TRS, and now everybody is following them. So how is defined equivalent square small field size? Because small field sizes, the dimensions, even if nominally the same, dosimetrically are not. So it's a kind of a rectangular, and it is geometrically equivalent. Square is then is the background for the definition of clinical field size. So it is a purely geometrical concept. And the same is also for circular fields. Again, purely geometrical concept. So we can actually transform circular field to rectangle to the square field with this simple equation, which is written here and is provided in the TRS 483. The next covered field is are detectors, which can be used for in small field dosimetry. There are many air-filled ionization chambers, usually mini or micro. Also, it is a common name. Liquid ionization chamber, not so common in clinics. Silicon diodes, diamond detectors, plastic organic scintillator, very important radiochromic films, and so on and so on. But no single detector actually stands out as having characteristics close to the ideal ones. Maybe I will later mention two of them, which are, to my opinion, most close to the ideal ones during the last part of the lecture. So, and then TRS 483 provides also characteristic of detectors for relative dosimetry. What should be stability, dose linearity, dose rate dependence, and so on, leakage. So you can find all these in a very comprehensive way in a TRS 483. So what would be requirements for, let's say, ideal detector, which we could use in a small field dosimetry? Very small active volume. Why? Because then we can minimize volume averaging effect. Water equivalency. It is actually impossible with the exception of liquid ionization chamber. If we have usual ionization chambers, they have air inside. If we have diodes or diamonds, they are too dense. Again, there is a perturbation effect. And as a third one, they should have a linear response and energy independence. It is also not always the case. So what they conclude in the protocol that there is no ideal detector. And they recommend use 2 or 3 different types of suitable detectors in a combination, one with correction factors above unity, one below, or something like that. They recommend small air-filled ionization chamber, radiochromic field, and unshielded diode, or as an alternative, diamond detector, liquid ion chamber, and organic scintillator. And it is not very common that clinics have, let's say, scintillator. Also, radiochromic film is not so oftenly used in clinic, although more and more nowadays, because it's a very promising detector and has a nice 2D visualization of the dose, possibility of visualization of the dose. And then, of course, very, I apologize now. I see a poll question. I forgot to mention that there will be a poll questions, yeah. So which dosimetry protocol do you use for small photon beam dosimetry on Linux?
We can now make small comments on this. We can see that majority of people are using IIA TRS 483. Some of them, which is correct. Some of them are using still 398. Even some of them are using 277. They're using TG report 155, and I'm wondering, I can see that 10% of people are using some other protocols. I'm wondering which are there. Probably some in-house made protocol. Božo, how will you comment this?
Yeah, it is maybe a little bit of a surprise because for small field dosimetry, the only valid protocol is 483, of course. As I mentioned at the beginning of my lecture, the use of 398 protocol, which is excellent protocol, but not designed for small fields, led to serious clinical accidents. So the main message would be, in the case of small field, please use TRS 483 without exception.
Okay, I agree. And now I think we can proceed with your presentation. And no, sorry, there will be another question. Yeah.
Yeah, there is another poll question. When performing small photon beam dosimetry, do you regularly use at least two or more different detectors for the same measurements? It is, of course, time consuming, but as we saw, it is recommended. It looks great.
Okay.
Beyond my expectations.
Yes, that's very, very encouraging to see results like this, which means that the majority of people doing dosimetry are using at least two systems for the dosimetry.
That's great. Usually, a physicist or who is doing measurements has very limited time for commissioning of Linux, let's say. Yeah, great.
Okay, I think we can now, Božo, you can now continue with your presentation.
Okay, thank you very much. I just need to find where are my slides now. Okay. So yeah, we need to properly set up the detector in the 3D full scatter phantom, in the proper orientation with respect to the beam axis, and following the exact protocol, either SSD or SAD. Because of this importance of the positioning, we need to do cross-line and inline scans to find full width half maximum, and with the help of these two 50% signals, we can define the beam center, and the beam center is also the point where the dose is maximal. If we make just a little mistake, maybe half a millimeter, we can underestimate the maximum and the profile a lot. And in the TRS 483, it is actually recommended, or there are provided guidelines regarding the orientation of detectors. So very important one, that cylindrical ionization chamber, either micro or mini, need to be put in perpendicular direction for measuring field output factors. What does it mean, perpendicular? Perpendicular is when the main axis, or the direction of the central electrode, is perpendicular to the beam axis. So we would say, let's say, in a horizontal way. For lateral beam profiles, it doesn't matter, although a little bit it matters. It is not allowed to scan in the direction of the central electrode, because you can average the dose and you will get broader penumbra than it is. But you can measure in this direction, and of course in parallel orientation, so-called parallel. Why parallel? Because the central electrode is parallel to the beam. But this is perpendicular direction, which is allowed according to TRS 483 for measurement of field output factors. Similar is provided, the data are provided for diodes, but in this case, only, let's say, parallel orientation is allowed. And now I think we have a third poll question. Yeah. Would you recommend parallel orientation of the ionization chambers for measurements of field output factor in small fields? If you remember, parallel is when the central electrode is parallel to the beam axis, and perpendicular is when the central electrode is, the direction of central electrode is perpendicular to the beam axis.
Okay, we can now see the very interesting fluctuation of the answers. Let's wait for additional 30 seconds to see what will be the final results. So the majority of attendees say that they will say no. They wouldn't recommend parallel orientation of the ionization chamber for the measurements.
It's very close. It's very close.
Very close, yeah.
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 So very interesting.
Okay, we will come back to these results later. Yeah, but you can now make a comment, Božo.
Actually, TRS 483 does not allow to use ionization chambers in parallel orientation. However, I had the same actually a problem with that, and we will come back later. And we designed a very large study to check, and you will get some answers at the end of the lecture. But yes, there are some problems. If you measure, let's say, profiles in a parallel orientation, and then you would need to switch to the perpendicular, how would you center your ionization chamber? Is one of the problems, but there are more. So we can now continue, because I would not like to run out of my time. So the most important, to my opinion, novelty in this TRS-483 protocol is that it introduced a detector-specific output correction factor. For broad beams, for output factors, the ratio of the measurements of the charge in the clinical and reference field is actually the same as it is the dose. But this is not anymore true in small fields, because there is no such equality between these two ratios. And it is necessary to introduce detector-specific field output correction factor K, which converts detector readings ratio into a true dose ratio, which we would like to have. And actually, TRS-483 provides a lot of very useful data. Let's say these are only for two ionization chambers. One is, let's say, a little bit bigger, semiflex. One is very small chamber, Extradine A16. And what we can see, correction factors for small fields are above unity. Why? Because ionization chambers have very pronounced volume averaging effect in small fields. So they would measure, we would measure lower dose than it is. So we need to correct with the correction factor which is above unity. And you can also see that this larger ionization chamber has very, very large correction factor for small fields. And this very small one is actually has actually correction factor below 5%, below 2 centimeters, also for fields below 2 centimeters. So because it's less pronounced volume averaging effect in the case of smaller ionization chambers. So we see we can measure down to, with microchamber, down to 0.8 centimeters, but not with semiflex. We need to stop at 1.5 centimeters. So just to comment, what are these empty places? In the protocol, it is explicitly written that we are not allowed to use detectors which have correction factors above 5%. So you see, all these published correction factors are below 5%. And the similar is also for solid state detectors. Here we have an example for synthetic microdiamond, but you see the main difference. Output correction factors are now below unity. For ionization chambers, they were above unity. And for diodes, it's not the case only for this one, stereotactic field diode, but for all diodes, they have output correction factor below unity for very small fields and above unity for a little bit larger fields. Still small fields, but a little bit larger. And protocol provides a lot of data for various solid state detectors. So you can see with these detectors, with solid state detectors, we can measure down to 0.4 centimeters. Field size is 0.4 centimeters. And now I think that we have already a third poll question. Which Linux-based IMRT, VMAT, SRS, or SRT treatment platforms do you use? It is a little bit connected to the remaining of the lecture.
So again, results are interesting. I think even some of the users are using Siemens, or rather old Siemens Artist machine for small field treatment delivery techniques like Siemens Artist, Encore, or Primus, for example. But I believe the distribution of answers is something that we could easily expect.
Yeah, I would say the same. So variant TrueBeam and Electa Versa HD.
Yeah.
Most commonly used Linux, modern Linux, let's say nowadays, and Halcyon, which is actually not so old, couple of years, let's say, is also on 20%. That is encouraging, I would say.
Yeah, and it's I think it's very positive that we can see that some of the users having the old type treatment machines, which are mainly used for the 3D conformal radiotherapy, are trying to use their machines for the advanced techniques, especially for the Siemens. So that's something that makes me happy, I would say, or makes me worry. What would you say, Bojo?
Yeah, it depends on the additional equipment. Maybe they have some collimator system, tertiary collimator system
Okay.
for small fields. I don't know.
Okay.
So let's continue to this last part. So actually, as I mentioned, we saw this recommendation for perpendicular orientation of the ionization chambers in the TRS 483. And then somehow we thought that it might be better to use ionization chambers in parallel orientation. The orientation which is not advised in the TRS 483. And so we conduct a rather large study with a lot of ionization chambers, different ionization chambers, mini, micro, and we compare on Electa Versa HD, Linux, and we compared output correction factors in both orientations. And what we found out that without any exception, output correction factors were lower if we used ionization chambers in parallel orientation, regardless of the beam energy and regardless of the filtration, either with flattening filter or without. And the same results we got for ionization chambers on the variant TrueBeam machine. Again, for all ionization chambers, output correction factors were lower in the parallel orientation than when we used perpendicular orientation. I assume that you will get those slides, so you can check it more thoroughly, or you can even ask for some additional comments, which probably can be provided. I don't know, the organizers will tell you. Again, the results were same regardless of the filtration and beam energy. A little bit more you can see here when we compared two ionization chambers, one that have, let's say, a ratio of the radial and longitudinal active volume 1, and the other, another which is a little bit prolonged, as usually ionization chambers are. And you can see huge difference if we look at the ratio of output correction factors when the orientation was perpendicular to that when the orientation was parallel. So actually, what was behind that? Why we conduct this large study? There was a kind of dispute, let's say, and a conversation after the TRS-483 was published. Some researchers claim that we would need to use also or allow also stem parallel to the beam. And okay, then we looked at the answer of the authors. They said that there was not enough data for the rotation parallel to the beam axis, and that's why it was not published and not recommended. But the latest report of the task group 155 of the AAPM, it was published, I think, last year. They say that such detectors can be used both with stem axis parallel or perpendicular to the beam axis. And specifically for fields below 1.5 square centimeters, it is recommended that these are placed with the stem parallel to the beam axis with specific correction factors to convert the reading dose as shown is TRS-483. What we can see now, without referencing or citing any study, they recommend parallel orientation, which is a little bit strange, but I agree with that. Another strange thing is to convert the reading to those as shown as TRS. There are no data in TRS-483 for output correction factors for parallel orientation of the ionization chamber. So when we read some documents, we need to be very careful. That is the message that I would like to share with you. And for those of you who are interested, you can read some of the papers which are the last slide. And now it's another for this lecture, last poll question. Would you recommend parallel orientation of the ionization chambers for measurements of field output factor in small fields? So again, the same question, and let's check the answers.
Well, looking at the preliminary results, I would say that they are quite surprising. What do you think, Božo?
No.
No?
I'm glad. I'm happy that I convinced the audience that parallel orientation is good.
Okay.
And I'm pretty sure that in 4 or 5 years, when there will be another issue of TRS-483, the parallel orientation will be recommended. Because now 2 or 3 more studies were published and will be published soon, which will actually confirm that parallel orientation can be recommended.
Okay, that's nice. That means that attendees has reacted to your presentation.
Great.
That's
I'm
very nice.
really glad. I'm really glad.
Okay.
So I would like to thank to my friends and colleagues with whom I do my researches for many years already. And thank you very much, organizers and all the participants. Thank you very much.
Thank you, Božo, very much for this very interesting presentation. I would just, before starting a third presentation, I would just remind the participants to put their questions into the Q&A box, and we will try to answer as much as more questions we can at the end of the presentations. So the next presenter is Dr. Josef Novotny from Department of Medical Physics, Nahomolce Hospital, Prague, Czech Republic. He's an expert in the special radiosurgery technique, that's a Lexel gamma knife brain radiosurgery. In his presentation, he will comment and he will discuss the use of IIA TRS 483 code of practice for Lexel gamma knife icon relative and absolute dosimetry. He will discuss phantom detectors and measurements procedures together with the new protocol for Lexel gamma knife. So, Joseph, the floor is yours.
Thank you, Herboye, and I thank you organizers to inviting me to this excellent webinar. This is actually a very humble question following Bojo, since dosimetry of gamma knife is much easier than on Linux, but I will try to do my best and share also some data which accumulated through years when I was involved in this field. So let's move on. So my goal for this presentation is to give a little bit brief introduction about gamma knife, especially dosimetric characteristics of for those of you who are not familiar with this equipment. I don't probably need to go deep in small field dosimetry issues. I think both presenters addressed basic issues very well. And I will focus on the Lexel gamma knife situation. We actually years ago ran some international gamma knife survey. So I would like to show you what were results at that time and a little bit comment what is, according to my experience, situation in departments right now. And then I would like to show our own experience here back in Czech Republic, in Gamma Knife Center in Prague, what we did in terms of to convert to TRS 483. And I would like to conclude with and show two examples of dosimetry audits. Audits are very important, especially for a small field dosimetry. It's a still relatively new field. So to have an independent verification of what we've done in terms of calibration is very important, and wrap up with very brief conclusions and summary. So let's move a little bit to introduction. Lexel gamma knife is a cobalt-60 based system. For those two models, Perfection and Icon, which are sort of current models, we're using 192 of those beams. And sources are focused on sectors. We have in total 8 sectors. Each sector holds 24 sources, and each sector can be in a different position to define beam size. We can have 4, 8, 16 millimeter, and we can also block those 24 cobalt-60 sources. So you can see we have actually very tiny field. We do love to use 4 millimeter collimator quite often, and our maximum field size is just 16 millimeter. We don't have anything else and any larger field size. We can actually treat only head sort of volume, so mostly we treating intracranial malignant benign tumors, vascular diseases, functional disorders. We can treat extracranial tumors such as jugular or chemodectoma, but we really should stop at around C1. If you have an ophthalmologist, you as a coworker, or you can ask him to join your team for specific patients. You can also do ophthalmoradiosurgery, so fix the eye and treat tumors such as uveal melanomas. Right now on Icon, it is available to have both frame and mask, but I think majority of centers still prefer to use the frame. So I can give you example here in Prague. We are a very busy center treating 1,200 patients per year, typically now. And out of this, only 30-40 patients were treated in mask last year. So that gives you the idea. This is a section which I think I can relatively quickly go through. It has been addressed that we do have, the science is a little bit behind. We as a physicist actually we're not working on the calibration protocols. Also, I think evolution and development of small field detectors was a little bit behind. So, for example, gamma knife has been used for several decades, but just recently in 2017, we finally got some new code of practice in order to properly calibrate those systems. I prepared this slide just to show, and I'm sure that I am still missing some equipment, but put technology, which probably everyone from us, I suppose, who is listening this webinar came across, because I think every big radiation oncology center now has to offer some sort of small field, some sort of radiosurgical or SRS treatment. So in the first line, we have those gamma cobalt based systems. In the middle line, we have several different Linux based systems. And in the last third line, I put other systems such as CyberKnife, Tomo, Vero system, and now this new Zapex. We should have actually a poll question now asking you what technology are you using. So please, if you can go ahead and answer, we are interested in your answers. I don't see, unfortunately, because I do see my camera, so I don't see the result for Lexo Gamma Knife. Will be something over like 20%. It's covered, unfortunately, by my camera.
You can move the camera left to right. You have the arrows on the camera.
Ah, I see. Okay, sorry for that. Thank you. Okay, I can see now.
Okay, so we can see that gamma knife and the CyberKnife are pretty much, let's say, at the same level, and that tomotherapy is a little bit lower. Is that something that we expected, Joseph?
Well, I don't know. It depends on audience. I would have to check who registered. I think now there are many different technologies available. I was expecting maybe more systems based on Linux based, because that's what quite often at radiation oncology departments offer, that they do treat patients on a daily basis, and then maybe a couple patients in the afternoon just for SRS, so they can use it for both, of course. So that's maybe I would expect more of those people voting.
Okay.
Okay. We
can continue.
All right. And as already addressed, it's a complex issue. It's not just we discussing mostly dosimetry protocols, detectors in those lectures here today, but it's also, of course, related to treatment planning software. And I think also it actually relates to us to adopt maybe new rules, maybe new logistic law, and possibly ask for mandatory audits and so on, so forth. This has been also addressed, what is small and what is big. We really not using the dimension of the field, but when students ask, so what is actually when you're raising this red flag, we usually say everything what is below 3 by 3, you should be start to be very careful and adopt sort of approaches for small field dosimetry, as Bojo very well addressed in his lecture. We're talking about those non-equilibrium parameters or characteristics such as occlusion of the source, non-lateral charge particle equilibrium, and detector is basically very large to what we in fact measuring. I think I don't need to spend too much time here. So on the left side, you see perfect situation when you go and measure your conventional radiation oncology broad large beams, and on the right side you see the situation when you're going to work at small field dosimetry. So let's move to Lexo Gamma Knife. And I wish I can say before TRS IAEA 483, which would mean, okay, now we actually Gamma Knife physicists, all centers are converted, we using 483, but it's definitely not true. At least my experience, I also work as a physicist consultant, starting up new Gamma Knife centers worldwide. So especially when I am traveling to countries in Asia, some European countries, I can't comment really now in detail about the United States. What is the situation? We still actually follow, because that's how Elekta does it, the 398 protocol. So basically the systems which are calibrated there are calibrated according to 398. I always make a comment, this is how I am supposed to do it, and what is correct way is really TRS IAEA 483. So if you want to change it, just look at what is the correction factor and multiply the value by the correction factor. And as it comes to Gamma Knife dosimetry, we have basically same tasks. We just have a very limited number of fields, and we do have very extremely small smallest collimator, 4 millimeter, but otherwise we really have to do absolute reference dosimetry, measure profiles. We don't measure PDDs. We have to measure relative output factors, and of course we should do some dosimetry audit or verify some complex dosimetry. Necessary to say is that there is a great support from Elekta. The software comes with profiles, so we really just checking the profiles. There are template data. You are not entering data. It is more or less the same with output factors. There are already data which were calculated by Monte Carlo. So I would say Western European and North American physicists, they have to measure. So they measure, they just compare. And if it is within certain reasonable tolerance, they just are happy. As far as I know, no one is really changing those default output factors. Hervoy, I think, already addressed that on Gamma Knife, we are not able to measure really in this standard water phantom. We don't have this classical aquarium which you filled up with water, and then you can put your chamber, do your reference dosimetry, or in larger phantom, you can scan. So typically, you have either this ABS, acetylbutylene styrene gray phantom, which you see on the left side, or more expensive and much better, I think, for dosimetry measurements is the phantom on the right side. This so-called dosimetry Elekta phantom, which is solid water. It's probably necessary to mention that there were also publications related to Lucy phantom. There was the work from Guy from US, which designed water phantom. And also there was a suggestion to do measurement in air as well. But I really want to talk about standard, and this is the standard. This is what you do see and how calibration is really done on site. I think the rest is more research and academic work. So we're using small ion chambers for profiles. We're using film dosimetry as a standard. And for output factor measurements, we try to use various detectors, which I will show in my presentation. Okay. We years ago ran the audit, the International Gamma Knife Calibration Survey. So I will present those results, despite they are and might be a little bit updated. I do hope that most, or at least over half of centers now converted and using IAEA TRS 483 calibration protocol, at least physicists in North America, Western Europe, I would hope. But it will be interesting to see when we also have those voting what you guys using. But let me first a little bit show you results. It will also show you that actually gamma knife, despite quite often, for example, in Japan, there is no medical physicist. In China, most of the time as well. But it's done by this consultant physicist from Electa. And when we ran this calibration survey, we actually found very good results. So even before 483, you will see that the gamma knife practice, as it comes to calibration, reference dosimetry, it was a good practice. So what we did in this 2009, 2012, we basically sent some questionnaire. We sort of ask users to irradiate 5 alanine pellets by 50 gray. So there was also some step-by-step procedure, what to do and why we doing this. This was the very brief questionnaire because our idea was less we ask, more chances that we get honest answers and that people would like to spend the time with that. So basically we were asking what you do for calibration, what protocol you use, what phantom you use, who is actually doing it, who did the calibration. Have you done any independent verification, any official dosimetry audit? And we also ask about what values for relative output factors are you using? And of course, question number one, what Lexo gamma knife is being involved. This is how irradiation of alanine pellets worked. We asked to deliver 50 to each of 5 pellets. If not possible, we ask at least for 3 pellets to be exposed. And user was supposed to use treatment planning software, calculate 50 gray, time to deliver 50 grades, and put it this specially made insert to the phantom and expose the pellet, and then so on for all 5 pellets if possible. Alanine dosimetry is not that frequently used. I was lucky that at the time I was in University of Pittsburgh. We had a communication, very close communication with the NIST, National Institute of Standards and Technology. Actually, Seifel Hack, one of co-authors of the TRS 483, was my boss at that time. So it was relatively easy. We were getting those alanines from the NIST. So actually values which were measured were like top-notch, really from standard laboratory. It's a sort of expensive equipment to buy these magnetic spectrometers to read those alanine. Alanine itself is cheap, but reading method. And I think we did pretty good job. Only unfortunate is that I didn't find time, and then I was already returning back to Europe to publish this data because the data were actually pretty solid. And as you could see, we surveyed 99 units in 91 centers over 27 different countries. Basically, at least one gamma knife from each continent where there is an installation, but mostly from North America, Asia, and Europe. Let me at least show you just a few results, really. I don't have time to go through this. This was like interesting result at the time, that despite TG51 protocol in the United States was the standard protocol to be used, at gamma knife, physicists still preferred TG21 compared to Europe and Asia, where we were actually preferring TRS 398 protocol already. So here we should have Paul voting. So if you can answer the question, this will be very interesting. I think Bozo had a similar question.
And I think it was a nearly similar distribution of the answers, if I'm correct. At least
Well, I
preliminary.
am actually extremely happy. I am positively surprised, because 70%, that's something that I didn't even expect. But probably we have to also consider who is participating on this seminar. If we add like +6, 7 hours and go to Asia, probably not many, especially physicists from like Gamma Knife or people who working at Gamma Knife, because as I was saying, my experience is that it's done by 398 protocol, for example. But I am very pleased with the results. It's showing actually that it is being implemented, and 70% is good.
I'm wondering how the results, how the protocol of other 8% looks like, and also what little bit surprises me that TG report 178 has 0%. That's, let's say, something that I would not expect. But okay, at least 70% of people are using the TRS 483. That's very nice.
Yeah, I'm happy.
We can continue. Okay.
Yes, please. Here I am showing that we're talking about small field dosimetry. So one of important aspects is what detector you use. And I always tell students, if you are alone, if you don't have any advice from senior physicists, just take that new code of practice. Look on those tables. There is a list of detectors. So before you decide what you're going to buy, you definitely want to have detector which has correction factors there. And it's also they're giving you suggestion, what is good and what is not good. So in fact, this table also served when this TRS 483 APM-IEA project was starting. I was asked, because they were aware that we ran this international calibration survey. So I provided the list of chambers which most Gamma Knife physicists using. We surveyed 100%. I mean 100 systems out of probably now 350 like the Gamma Knife systems worldwide. And you can see what sort of chambers are being used. Why 33110? Then I will at least comment, because Elekta is using that one. So they probably recommend that one as well when users ask, so what should I buy for calibration when I want to measure my dose rate? And A16 also was at the time very popular. I think PRO5 is more or less replaced chamber probably. That's a kind of historical chamber which used to be used at the Gamma Knife centers in United States. Here we go. I mentioned that we were having actually good results. For those audits, usually you do accept relatively reasonably large discrepancies. So when we plotted planet and measured ratio, all Gamma Knife systems were within ±4%. Actually, most of them were ± within 3%. So that's what we considered as being very reasonable, good practice. But there were sort of like some systematic shifts seen. So those that used actually those older protocols, which were taking into account material of the phantom, because this ABS phantom is not really exactly water equivalent, they were having distribution which we want to see, like ±. And those which were using approximation with TG51 or TRS398 and protocols which are based on this IEA protocols, they were having some small systematic deviation, but still reasonably good results. Actually, we were pleased that we didn't find any Gamma Knife which would be really like over 5% off. As it comes to, I already, I think, mentioned this, as it comes to relative output factors, here we have it was 100% sites using basically Elekta default values. So I can mention what we did. We use this 483. In our case, it's this first approach, this machine-specific reference field. And again, I can speed up here because Bojo and also Hervoye partially went through this. So following basically what we've been doing till now, we do calibrate using NDW, we correcting reading, but there is this one additional parameter, this K factor, which is correcting for everything. So you just go to TRS 483, you do find your detector, you check what sort of phantom you're using, and actually even what gamma knife you're using, if it is perfection or icon, or if it is also the order system, this C generation gamma knife. So very straightforward, very easy. Similarly, for relative output factors, you use the ratio of readings, and you also multiply it by K factor, correction factor, which is specific to the detector and to the field size which you measured. You already saw this slide, so I can quickly go through. So in my situation, I'm using PTW 31010. You see the copy from TRS 483, and I do have both phantoms available. So I was actually thinking that it might be useful, and just for myself and for maybe other people, like for this webinar, we also presented this in a couple meetings, that it might be useful to see what different combinations, like 2 different phantoms, 2 different protocols. So TRS 398 and TRS 483, and 2 different phantoms gives you 4 different combinations. So what sort of errors we looking at? And I think for us physicists, of course, it's a relatively large error. No one wants to be systematically like 2% off. But in terms of clinical implication, you do see that those errors are actually very minor. So for us specifically, what I was doing correction in my treatment planning software by 1.44%. So since certain day, I told our doctors, since beginning tomorrow, this is gonna be a very small change in the dose, and I gave them white paper to explain what has been done and why it has been done. I did have available microdiamond detector, so I used microdiamond detector to verify and measure those relative output factors. So you do see again for 4 and 8 millimeter those corrections in the table, which is taken from 483, and we did similar measurement. So 2 phantoms, so different measurements. Let me a little bit address the work which started over back in Pittsburgh. So we're looking at like 2010, and I used the different detectors which were available. Some of them we were aware that they are not appropriate detectors to measure, especially 4 millimeters. That's why I switched to 4 millimeter, because here is even exaggerated how big error you can make. So especially when you look on the x-axis and with the increasing volume, if you would use like those small microchambers and compare it with Elekta default value, which was calculated by Monte Carlo, you would end up with huge errors, around 20%. I have values in the next slide in this presentation. So we look at the various detectors, and to us, useful detectors are stereotactic diode. I actually liked microdiamond detector. We also used films That's a cumbersome work, but we actually end up with reasonable results with the film dosimetry, despite it's a time consuming and you have to be careful of many things. What is absolutely unacceptable for those tiny little fields are, of course, those microchambers and some huge detectors as a large alanine dosimeter or some larger diamond detectors, is standard diamond detector, which PTW is offering for a long time, and also some diode detectors. I am missing here scintillator, which is, I think, promising detector. That should be the good one to be used. So don't take this, please, as a overall list of detectors. It's basically what was available, because that's also, of course, always problem that we have to use what is available in the department. And here I am showing this, just always show this to students, that if you use basically wrong detector in small field dosimetry, you can end up with terrible errors. And if you would introduce these values in the treatment planning software, that can be a huge disaster, really. We would end up with errors over 20%. So these data were mostly measured to give it as a memento and to tell people, please be careful when selecting detector. Now I think TRS-483 is giving you those tables. So new users, new physicists coming in the field can read what is being suggested and what is not being suggested. Just quickly show our results with microdiamond. I mentioned that we did it for both phantoms and with and without correction. So TRS-398 versus TRS-483 again actually end up with I think reasonable results. I do accept maybe a little bit more deviation when it's coming, especially to 4mm beam. And to wrap up this portion of presentation, we was very straightforward to recalibrate and move to TRS-483. We did see relatively small deviations for both reference dosimetry and relative output factors provided by Elekta. We used PTW 31010 and microdiamond detector. I was thinking we should have actually poll voting after a few slides, but if we can pop up it now, it would be maybe useful when I start to talk about dosimetry audits. So is it possible to get that last question, last poll now? Yes, excellent. Thank you so much. So I want to address and wrap up my presentation with audits, but let's first ask you to answer if you have ever participated in a national or international small photon beam dosimetry audit.
I think the preliminary results are as expected, because we know at this moment there are no, let's say, organized small field dosimetry audits like it exists for in the program of IIA, which have, I think, postal. Previously it was postal TLD, and now it's RPL, I think, or OSDL. I'm not quite sure for the conventional radiotherapy beams. Such a program still doesn't exist by the IIA, so it's quite, I think, quite normal that we have a majority of people which were not participated.
But I'm still pleased. I don't remember exactly what was the result from our international gamma knife survey, but I think it was below 10%. Yes, that people actually said, yes, we participated in something at least. It was also like, has your colleague measured, even unofficial, some independent verification of the calibration. So at least 25%. That's actually better than what I expected. Yeah.
Yeah, quite well. actually expected that this yes answer will be below 10% or maybe below 8%.
So I'm pleased, despite it should be, of course, much higher. Well, let me quickly, because I may be running a little bit out of time, so let me quickly show what we did. Also, it's addressing and showing two different ways how the audit can be run. And I think it's mostly important we're doing it for the patients, right? We don't want to really treat our patients by the bad dose, by wrong dose, but it's also covering, I think, our back. So it's protecting our practice as us medical physicists, and of course the whole department and the hospital. I think dosimetry audits really can catch those major terrible errors, and we should sort of mandatory implement them. I am happy that in Czech Republic we do have this National Radiation Protection Institute, and it is mandatory. Before you starting new center, you do have to go through the audit. If you don't do so, you will be penalized, and it's a big problem. Basically, it would be very bad, sort of illegal behavior considered here. So I'm happy that I live and work as a medical physicist in country which implemented it as a mandatory. So I did this audit, which is on-site audit. It means people actually physically come, physicists come with their PTW Unidos, they come with their detectors, and they physically measure. So you do see the people, you work with them, and you appreciate definitely them that they doing it to check your data. And the second is the other example, which is post audit. I spent 5 years in United States, actually used this MD Anderson SRS head Phantom for cyberknife commissioning and for gamma knife commissioning as well. So I knew it. I knew it's nice and working. So I actually asked to mail it to me. So it doesn't matter that you live in Europe and work in Europe, they can do it for you. You just have to pay for that, pay for the service and pay for the FedEx or whatever service you using to transport it. I will not go through details. I will just quickly address what our Radiation Safety Institute is doing. They check basic calibration in that Phantom. So basically double check what I've been doing for dose rate measurement, but they have also this anthropomorphic head. So it's a Alderson random Phantom sort of based. So you have those cuts, and they have two drills for two ion chambers, and they can also put film in it. Those chambers are big, so you have to contour volume of the chamber for those gradients. Impossible to use them as a point measurement, so there must be used as a mean dose measurement. So that's what you're reporting from the treatment planning software, and you can also insert dosimetric film between those plates. And I will just quickly go through. You do normal planning. Basically, it is really end-to-end test. You follow all steps of the patient. That's the point of these audits. So you fix it in the frame, fix it in the mask, for example. You image the Phantom the same way. You import data, you plan, and you finally deliver what you plan it. So exactly what you do to your patients. So here you can see some results. We actually ended up with very, I think, reasonable discrepancies. They have relatively much closer interval, which they accept compared to MD Anderson. Here's some results from 2D distribution from the film and from profiles. Let me quickly also go through this MD Anderson Phantom. So I was saying that they will mail you. So you will get the big box with this guy. It's a plastic head which you fill up with water. And you basically have those two inserts. One is for imaging. This is your target, this spherical. This ball is basically representing your target. They will tell you exactly what to do how to plan, what dose to deliver. And then you change, when you are ready, you change to this dosimetry insert, which has 2 orthogonal films and 2 TLD capsules. And you deliver the dose basically as you plan it in your treatment planning software. As mentioned, this Phantom, of course, can be used on any technology. Yes, it can be used on CyberKnife, Gamma Knife, Linux-based, doesn't matter what technology you're using. Just quickly again, try to move on to the end of my talk. So we ended up with quite a difference between 2 of these capsules, but on the mean average from those 2 capsules was like 2% off. So still, I think, very reasonable result. Here you can see that they do accept ±5%. And from films, I can show those profiles. They also were relatively reasonable. I didn't like a little bit offset on this very last profile, but was not any like significant, was still within tolerance. But this is what basically they can provide. So it leads me to very general conclusions. As it comes to Gamma Knife, and probably based on voting today, I think we heading there. We, despite TRS 483 is available since 2017, we slowly implementing it in clinical practice. In Gamma Knife, I actually would be a little bit skeptical. I would bet that probably at least half of centers still are not running on this TRS 483. And as Bojo addressed, I think manufacturers relatively reacted very well, and they trying to please us with various detectors. But we as a researchers, academic physicists or clinical physicists should evaluate properties and should still work on testing and optimizing and maybe refining corrections factors as well. I am sure there will be second edition and more editions of TRS 483, so possibly new detectors and maybe refining correction factors will be published there. And also 2 more important things, I think, which are not that technical. It's this logistic, basically, to implement those dosimetry audits, and also education. This is what we're doing today. I think those kind of webinars are also important to talk about it and inform, especially young physicists. So that's it for my presentation. Thank you very much. I will sort of finish with this allegoric picture. I think we are somewhere in the middle of the wall. We maybe are already close to the summit, like me here on Dent de Jeanne, close to Mont Blanc. But we're still climbing. We have still some portion to climb on this and reach the summit of small field dosimetry and TRS 483. So thank you for your attention.
Thank you very much, Josef, for a very detailed presentation for this special technique. I'm sorry that we don't have more time to see maybe some other special techniques used for the radiosurgery, stereotactic, and other stereotactic treatments. There were questions in the Q&A box. Majority of them were answered by Bojo, so we can now, Josef, if you click at the QA box, you will see the new questions. There is one interesting question. What is from Irhas? What is used to limit the radiation timer when measuring dose rate based on modality, Gamma Knife machine or electrometer? How?
Say it again.
What is used to limit the radiation timer when measuring dose rate based on modality, Gamma Knife machine or electrometer?
What you're using to for timer?
Yes.
Yeah. Well, we measure dose rate the way this way. You basically set up long treatment time. You drive your Phantom inside radiation unit, and then you're using timer on your electrometer. So basically, like in our case, PTW Unidos, we're using 60 seconds typically with this PTW 31010. This is also what I do when I work for Elekta. If Elekta provides, which they sometimes do, a 16 chamber, we're using 2 minutes, so 120 seconds. And usually it's pretty stable reading. So you read like 10 readings and you are actually done pretty quickly.
Yeah, I agree.
Yes, that was the question.
Yeah, I think that was the question. Actually, as I understood it, the question was, are we using integration with the electrometer, or we are simply pressing the measurement start before the entering the...
That's what I am using when I am checking the timer of the Gamma knife. So when I am checking timer, I test like for 1 minute, 5 minutes, 10 minutes, and you can go even higher and see the linearity of timer. So that would be the situation when I would use the timer of Gamma knife, because that's what I am actually, QAing. That's what I want to address.
Okay, thank you. And the second question that was left, do we need to apply TRS 483 correction factors for the patient-specific QA measurements using microchambers? Well, that's very interesting questions, but since the I would say treatment fields are usually superposition of many different fields coming from many directions, I'm not quite sure if we can really use the correction factors, because they are meant, or they are constructed or derived in a special very defined geometry.
Yeah, I remember when Saiful Haq was coming back from those meetings, we were having multiple discussions about this topic. And that's exactly what I told him. I just can repeat your words, and I can even highlight it with the newest inverse treatment planning software called Lightning for specific targeting tumor which has, let's say, 3, 4, 5 cubic centimeters. With this inverse treatment planning software, you sometimes use like 50, 60 isocenters, which have very bizarre shapes. They are really very close now. It's almost like painting the dose to the target. And from target to target, it's very different, it depends on constraints, you said. It depends on the shape which tumor has. So I don't think it's actually that it will be possible in any time in the...
Actually, maybe some correction, patient-specific QA corrections could be done maybe when using a single collimator, maybe in some cases.
That's one I can imagine, possibly.
But that's not close to the clinical situation in which we have, as you said, many isocenters.
Most of the time,
Okay, thank you for your answers, Joseph, and once again, thank you for a very, very detailed presentation. I would like to thank the Bojo as well for the very detailed and very good presentation. And I hope not just clinicians but also researchers have gained something from this presentation, from this webinar, and I hope there will be possibility to apply that in their research and in their clinic. Regarding the question and answers, a lot of questions were answered by Bojo, and they can be seen in the answered box of the Q&A. So I hope that participants have read all the answers. I'm sorry that we cannot prolong this to even more discussion about special techniques and dosimetry, but we have a time limit we have to obey. So at the end, once again, I would like to thank to the presenters, Josef Novotny and Božidar Casar, and also I would like to thank to the organizer from the SAK SEN, and message to all attendees, stay tuned to the Eurados webinars because researchers and clinicians could hear, I think, very nice and very interesting thing from the activity of the Eurados community. So that's all from my side.
Thank you very much.
Thank you very much, Hrvoje.
Thank you.
And
thank you very much also participants.
Exactly.
Attention.
Yeah. Thank you to them as well.
Mm-hmm.
Okay. Goodbye.
Goodbye. Take
Bye.
care. Bye-bye. Bye-bye.
Bye. See you.
See you.